ridiculous, but if not, you could still grasp it in one day. Okay, so we have this thing called the extreme value theorem, which sounds fancy, but it's not. It says if a function f is continuous over the interval a to b, then f has at least one minimum value and at least one maximum value on a to b. So if we look at this graph, even though it looks sort of crazy, it's still continuous because every time there's like a hole, there's still like a value there, right? So even though there's a hole here, we still are giving it a value. So it's technically continuous, even though we can't we have to lift up our pen. So since we have to lift up our pen to draw this graph, it's not differentiable, but it is continuous. So we can make that, right? Not differentiable, but yes, continuous. Ooh, focus. Okay, so it's pretty simple. It just says there's one minimum, at least one min, and at least one max. That's what the extreme value is. So if I give an example, right, if I'm drawing like this little, mountain, there's at least one minimum. So if we look here, we have two minimums. And here we have three maximums, right? So those are just like the top and bottoms of the hills. Another tricky one is like if I just have a straight line, they're like, well, where's the min and the max? Well, technically here, every point is a min and a max. Right? Like sort of like, you can make a joke, like if you're a only child, you're the oldest and the youngest sibling. Okay, so you'll have different vocab words. We'll have global versus local, or absolute versus relative. So they mean the same thing. Global is the same thing as absolute. Local is the same thing as relative. Just different teachers or textbooks might use different ones. So I might jump in between the two. It's sort of similar to like how Spanish, you can say like andar or caminar. Both mean to walk, right? It's just like a personal preference. Or like what you grew up with. Okay, so if we're looking at this graph, I'm going to do the absolutes in blue, and I'll do the absolute in blue, and then I'll do the relative in orange, or the local. Okay, so it's always easier to start with the absolutes or globals. It's just the overall. Oh, my blue's dying. Okay, so if I look for the absolute minimum, it's right here. It's the absolute lowest. So I'm going to label that as absolute min. And then if we look for the absolute max, it's right here, because this is the tallest point on our domain. Right? Our domain is A to B. So this is A, this is B. And then we can do our relatives. So if we look here, this is a relative min. Right here is a relative min. Here's a relative min. This one is not a relative max because it's not a point. Not rel max because not a point, right? It's a hole. And then this one right here is debated in the math community. So you could say it's a relative max, or you could say it's nothing. So some people argue like, okay, well, it's relative to these points, it's a maximum. But some people say, since there's nothing on the other side, it can't be a relative max. So depending on your teacher, I usually would say it's a relative max, but I wouldn't count it wrong if you forgot it. It's a pretty 50-50 split in the math community. It's sort of like that black and blue versus white and gold dress. So I'm going to label them as relative maxes if I see them, but if you don't, it won't be counted wrong. Okay, so we always have one absolute min, one absolute max, and then we have the rest. We can have unlimited relative. Okay, so here we go. Now we're gonna write it, instead of just labeling on the graph, we're gonna write it like a little more formal. So it says find all extreme values, identify the type and where they occur. So again, it's easier to start with the absolutes, the globals. So we have our min and max there. So I'm going to say absolute min at 1, or of 1, at x equals -3. Right, so it's saying my value, my y value is 1, and it's happening at x equals -3. Let me use a pen. And then similarly, you can say absolute max or global max of 5 at x equals 0. And then this one can't be anything because it ends on a hole. Same with this one. So we're going to have one more relative min. So we have rel min of 2 at x equals 1. Right, so pretty much when you're thinking of relative, you're thinking of like relative to the points around it, right? So relative to the points around this guy, he's the lowest. So he might not be, right, if you think of like racing, relative to his team, he's the slowest, but relative to every team, he might not be the slowest runner, right? All right, and then for this one, we actually don't have an absolute min because it ends on a point. But we do have a relative max. So we can say, I'm just going to put this here for your notes, but you don't have to write it down on a test. No absolute min, and then we have absolute max of 3 at x equals 1. And then try and see if you could find, there's 2 more other critical points. Let's see if you can figure them out. Oh yeah, actually this is -1. Good correction. Okay, so we have relative min of -1 at x equals 4. Right, and then the last one is relative max of 1 at x equals 1, which is this one right here. Right, and the other ones don't really count because there's holes. And then this one, even though it looks like there could sort of be a dip, it actually doesn't, it never dips. Like this isn't quite a max and this isn't quite a min. It actually like levels out and then goes up. So this one isn't anything, even though it sort of looks like the difference of that would be if it was more like that, rather that. This one, there's a max and a min. This one, there's neither. So be careful with those curves. All right. So we're going to come back to the front page, but let's write a definition real quick. So we have critical point, which we sort of talked about, but now we have a official definition. So a critical point is a point that has the possibility of being an extrema, which is a max or a min. Right? So that's a lot of blah blah words, but essentially it's saying like it could be a max or a min. We don't know if it is, and we don't know which one it is. Okay, so how do you find a critical point? The f prime of x does not exist, or f prime of x equals 0. Right, and again, this is in math language. So what does that mean in English? What does it mean in the real world? It says, right, aka the derivative doesn't exist, or it equals 0. right? That's easier to understand than this. I mean, we should know that f prime of x means derivative, that little apostrophe, or dy dx, but the real thing is the derivative doesn't exist or it equals 0. So let's look back at this front page and let's look at a picture. So if we're looking at all of the relative maxes and mins, let's just draw them at first. So it doesn't really matter now, like I'll do the absolute, but it's not that important. We have an absolute max, a relative min, relative max, relative min, relative max, and then there's actually no absolute minimum here because the graph keeps going down forever. So the trick that they want you to connect, like the most important thing with derivatives, is understanding what is the derivative at these points, right? So let's write this to the side, right? Big question. What is the derivative at critical points? Mins and maxes. So we know from before that a derivative is a tangent line. So if we were to draw the tangent line to this, it would actually look like this. Right? If we were trying to draw the tangent line like right here, it would be like a straight up and down line like that, right? If we were to draw the tangent line here, it would look like that. But at our critical points, we can clearly see, like, what is the derivative? What is the slope of that line? Very nice. It's 0, right? So the answer is, or does not exist. That's the tricky one. Right here, we actually can't have like a slope because it's like a cusp. So this one would be like does not exist. So f prime does not exist, and all the rest of these are f prime of x equals 0. Derivative is 0. Slope of the tangent line is 0. dy dx is 0, right? So that's like the secret. When we're at a maximum or a minimum, our slope is 0. Our rate of change, it's not changing anymore, right? Okay. So let's do the actual math part, right? Everyone's favorite part. Okay, so find all critical points, right? Before this lesson, you'd be like, what does that mean? What do you want from me? It means that I want you to find me possible maximums and minimums. So the key to this is, right, taking the derivative. So I'm going to take the derivative of f prime of x. Hopefully you guys can do that. So we pull the 3 down. 3 times 1/2 is just is 1. So we have x squared minus 9, right? So I took the derivative. And now I need to set it equal to 0 or set it equal to does not exist, right? So if I set it equal, there's no number where it doesn't exist, right? Like, because there's no fraction or negative square root. So I'm just going to set it equal to 0. So I have 0 equals x squared minus 9. And then I need to solve it, which is factoring. Hopefully you know this off the top of your head. If not, you can work on your factoring. You could put it in the graphing calculator, but you should be able to do this pretty quickly. That's why we harp so much on factoring in pre-calculus and all the classes before, so that this doesn't stop you, right? This shouldn't stop you from solving this calculus problem. So then we have x equals -3 and x equals 3. And if we went back and plugged that into the equation, it's still like a real solution. Like sometimes when you put the final answer back into the equation, you get like a negative square root, so it wouldn't actually count, right? These are like possible critical points. So let me show you on the calculator just so you can like get some context as to what's happening. So I have 1/3 x to the power of 3 minus 9x plus 24. Let's look at it from -5 to 5. Okay, we need to make it bigger, our y values. Oh, okay, even bigger. Okay, so we have this beautiful polynomial, which was one of our units. And we can see at -3 and at 3, we have like the top of a hill and the bottom of a valley, right? So even if I didn't have a graphing calculator, I was able to use math to tell you something about the graph. Does that make sense? So that's like what we're trying to do is like, we don't know if it's a maximum or a minimum yet. We will, but you can at least tell me there's something important happening at -3 and there's something important happening at 3 of the original equation, right? This is the original equation, this isn't the derivative, but we use the derivative to find that out, right? So these are important, right? Critical, same word, critical points. Something important is happening at -3 and 3. Turns out it's a maximum and a minimum. Okay, so let's look at 4. This one is a little trickier, but not that bad. So we have g prime of x. We're going to actually rewrite this so that it's prettier to take the derivative of. So we're going to write this as g of x equals 4 minus x squared to the power of -1/2. Right, so I just rewrote it. I haven't taken the derivative yet. I'm just writing everything in an exponent, right? So when it's in the square root, we get the 1/2, and the negative was because it was on the bottom of the fraction. And now I can take the derivative, so g prime of x, we pull this forward, -1/2, 4 minus x squared minus 3/2, because -1/2 minus 1 is -3/2. And then we can't forget our chain rule. We have -2x. So sort of a lot going on, but you've all done it before, right? So derivative. On the side here, I'm just writing what I'm doing so you can go back and understand the steps. I did the derivative. The first was a power rule with fractions. And then it was a chain rule, in case you forgot. So now I'm going to rewrite it again to make it look prettier. These negatives are going to cancel out. And then the 1/2 and the 2 sort of going to cancel out. So I'm just going to rewrite it to be x over 4 minus x squared. This whole thing is to the 3rd power, and then you take the square root. So I turned it back from fraction to something like prettier that we're more familiar with. All right, we're almost done. Okay, so we have 2 more steps, right? We took the derivative. Now what's our next step? Setting it equal to 0 or does not exist. So if I set this equal to 0, that means the numerator is 0, right? We sort of did this in 3.6. So if I set it equal to 0, that means that x equals 0. And if I set g prime x to does not exist, that means my denominator is 0. Equals 0. Okay, so this one we're already done. This one, if this whole thing is 0, that means that the thing inside the parentheses has to be 0, because it would be 0 times 0 cubed and then the square root of that. So I'm going to just set 4 minus x squared equal to 0. And then you could factor it, or you could just know in your head that it's plus or minus 2. Okay, so I have to re-record the end for this. So we set the top equal to 0, and we set the bottom equal to 0. And before I just set this equal to 0, but I sort of want to go into more detail, right? So this is the square root. We're going to square both sides. So then we get 4 minus x squared to the 3rd equals 0 squared is 0. And then we take the cube root of both sides. So then this becomes 4 minus x squared, and the cube root of 0 is still 0. So that's why I set this equal to 0. And then we get x equals plus or minus 2. But the trick with this question is that this isn't the actual answer. The reason why is because we want to plug it back in, right? So if I plug this 2 back into the original equation, I get 1 over 0, which is undefined. So we're not allowed to put in plus or minus 2, right? So this is a critical point. Like it could have been a max or a min, right? It was a suspect, but it ended up not being like the numbers that we were looking for. So our only solution right here is x equals 0. And if we look at the calculator, one over the square root of 4 minus x squared. Let's change that to negative 5, 5, negative 2, 10. All right, we see we have this smiley face sort of cup thing, right? And so we have a minimum right here. You sort of can't tell, but it's the bottom of the hill. And then at 2 and negative 2, we don't have a value. It doesn't exist. So we only have one critical point. Right there. Right? That's our only extrema.